began with our sort of solutions to markup precision processes, and we looked at dynamic programming, which is a method that dealt with model-based solutions to markup precision processes. Now in this lecture and the next lecture, we're going to sort of take the same path we took through dynamic programming. We're going to start off looking at how to evaluate policies, and then we're going to move into how to use those to control how to find the optimal solution to markup precision processes. We're going to break it down into two pieces this time, so it's going to take 2 lectures to cover this ground. But what we're going to do, which is very different from dynamic programming, is we're going to deal with the model-free case, where the agent doesn't know the MDP it's in. It isn't given a description of this MDP, it doesn't know the transition dynamics, it doesn't know the reward function, and yet it still needs to solve this thing. We're going to find that we can still come up with methods very similar to dynamic programming solutions, where the agent, despite this lack of knowledge, is able to solve this problem very effectively. Okay, so this lecture is basically going to be divided up into 3 main parts. So after the introduction, we will look at 2 of our sort of principal solution methods to model-free reinforcement learning. These are really core methods that are very widespread. So the first core method is Monte Carlo learning. This is a very simple, straightforward, very practical approach to reinforcement learning, to model-free reinforcement learning. Then we're going to move on to temporal difference learning. So the difference between these is essentially Monte Carlo learning looks all the way to the end of the episode and learns from complete episodes, whereas temporal difference learning just looks one step ahead. And what we're going to see in the final section of today's lecture is how there's actually a spectrum between these 2 extremes. There's a whole spectrum of model-free reinforcement learning algorithms that goes from this sort of looking all the way to the end of the episode as in Monte Carlo learning, and just one step ahead as in TD learning. Now, if you're looking back at Sutton and Bartow at the end of this and want to sort of go over this ground again, what we're essentially looking at in this lecture is the prediction part of 3 of the chapters. So chapters sort of 5, 6, and 7 of Sutton and Bartow we're going to cover in this lecture and the next lecture. But we're going to do it first with prediction and then with control. In this lecture, we're not worrying about control at all. Okay, so last lecture we basically wanted to deal with this problem of solving a known MDP. Today we're doing what we call model-free prediction. So specifically, what do we mean by that? Yeah?
Can you pull down the whiteboard down?
Yeah. This?
No, the one on top.
Ah, I see. Yeah, you're right, that's not there. I didn't even realize it was on there. I see. Okay. Slightly less scruffy looking now. So specifically what we're trying to do is we're trying to estimate the value function of an unknown MDP. So the agent's dropped in to an MDP, it doesn't know the dynamic, doesn't know the reward, but it has some fixed policy. And we want to know how much reward is it going to get in this MDP following this particular behavior. So let's say it's thrown into some grid world, it's moving around uniform randomly, and we want to know, well, how much reward is it going to get? Well, we don't know the reward function, we don't know the dynamics, what do we do? Well, we need to do some machine learning. And then in the next lecture, we'll actually use, just as we used policy evaluation in the last lecture as a building block for control, policy evaluation methods were a building block that we use to do methods like policy improvement and then leading to methods like policy iteration. We'll do the same thing next lecture. We'll have the analogs of all of those techniques that we came across in dynamic programming. So we'll actually use, if you understand how to estimate the value function of this MDP, we'll be able to use that to do control, which is to optimize the value function of this unknown MDP. Okay, so today we're sort of focusing on this model-free prediction. So the MDP is given, the policy is given, how much reward are you going to get? Sorry, the MDP is not, it's unknown. How much reward are you going to get? Okay, so if you remember from the introduction, we had this sort of this rat, and it was thrown into this world, and it saw some lights and a lever and a bell, and then got a shock. So this is how you should be imagining this model-free setup. It's like you don't really know how the world's going to work. You're just a rat. You're wandering around this thing. Maybe it's got some idea of what state it's in. Like this could be the history of the last 3 things it's seen. And now it just needs to make a prediction for the last 3 things it's seen. What is it going to get shock next, or is it going to get cheese next? And you all came up with some predictions last time about what was going to happen here. So this is the sort of example maybe would be useful to know. But just like the rat, we don't know the transition dynamics. We don't know the maze it's been dropped into. We don't know what's going to happen when it presses these different things. It just has to use trial and error learning, try out some different strategies, see what happens, and learn how much reward is it going to get by following these particular policies. Okay. So that's sort of the agenda for today. So we'll start off with our first sort of major solution method for model-free RL, which is Monte Carlo learning. So the basic idea of Monte Carlo learning is what's going to happen is we're going to drop down our rat into its maze or into its world, and it's just going to try some stuff. It's going to wander around for a complete episode of experience until it gets electrocuted or gets its happy piece of cheese or whatever happens to it. And then it's going to say, well, it gets some reward for that episode of experience, and it's going to just learn that the value function is basically averaging over those episodes and how much reward it's got. So it learns directly from that experience, from complete episodes of experience. It's model-free, which is our goal. And it doesn't bootstrap. We'll see later on in this lecture methods that bootstrap, more like dynamic programming. So Monte Carlo has to wait all the way until it's seen complete trajectories of experience before it does any learning. And it uses the simplest possible idea you could come up with, which is basically that the value function from any state is just the mean of the returns it's seen from that state. So if it started in a state, it's had 2 episodes, and in one of them it got 10 reward, and in the other one it got minus 10 reward, we now estimate the value of that state to be 0. Okay. There's a major caveat to all this, of course, which is because it learns from complete episodes, we can only apply Monte Carlo learning to episodic MDPs. That means MDPs that always terminate, and so the experience that the agent receives comes in complete episodes. If the MDP goes on forever, it's not directly applicable. You can approximate it, but it's harder to use Monte Carlo learning, and we'll use the methods from the second half of this lecture to deal with that continuing case. Okay, so how do we actually use this? So we're going to have some input. Basically, we're going to see some episodes of experience. The rat's being dropped down. It starts off in state S1, takes action A1, gets some reward R2, and so forth until it finally terminates in state ST. And that's just by following this fixed policy. And if we ran a different episode, we get the second episode, we get another one of these sort of strings of state actions, rewards, and so forth. Well, basically, that's our input, and the question is, how do we use this to generate a value function? And note that we can also do this in a Markov reward process. This is just coming back to the notation from lecture 2, that because the policy is sort of given, we can always flatten our Markov decision process into a Markov reward process. So in fact, we don't really need to even worry about actions. We can still just ask the question, how much reward will this thing get in this Markov reward process? Okay, but we want to take these episodes of experience and output a value function. So how do we do that? That's what we're going to look at. And Monte Carlo can be used, in addition to using it for prediction, it can be used for control, which is what we'll see next lecture. And the control problem is now these episodes of experience will come in, just these samples of what this rat's done on it following this policy, and it wants to learn, well, what's the optimal way to behave? What's the optimal value function in the optimal policy? Okay, so we're doing prediction. So we're going to start off with this definition of return. So hopefully everyone remembers that the return is basically the sum of the discounted rewards from now all the way to the end of the episode. That's the return. And so we're following this policy, we see our episodes, and the value function is defined to be the expected return. This is the formal definition of value function, just that the value function from state S is the expectation under policy pi. That basically means if we follow pi from now on all the way to the episode, so all of the actions are drawn from our own policy. This is the expected return given that we start in the current state. So all we're going to do is we're going to replace this expectation with the empirical mean. That's how we're going to estimate the value function. We're going to replace this expected return by the empirical mean return. So it's the sort of simplest approach to machine learning. So you've seen this many times before, hopefully.
So here T is, the capital T is given as finite.
We're assuming that this is an episodic MDP, and so all episodes terminate. Capital T can be random, so it doesn't need to terminate at the same time step. But we're assuming that this rat's going to wander around, and at some point, its episode is going to terminate. We'll call that time step capital T for that episode, and so you get some return, which is just all the rewards up to that time step. And then once it reaches that time step, we say the episode's finished, and now we want to learn how to do update our estimate of the value function.
So in general, this value function can also depend on time t, small t as well.
The value function doesn't depend on t because of the Markov property. So the state, remember, characterizes in the Markov decision process, the state characterizes the entire history, gives you all the information about the entire history of everything that's happened.
Well, I mean, if capital T is fixed, then, for example.
So you're saying that the value function depends on little t or on capital T?
If capital T is fixed, then the value function should also depend on, for example, small t minus capital T.
Yeah, capital T is a random variable,
it's random.
and it's also obeys the Markov property. So the
Okay.
termination of the MDP is also Markov.
Okay.
And so that means that all we need to know is the state. So it's just, you can also think of this, you don't need to think of this as anything special. You can imagine just a Markov decision process where there's one special state, which we're going to call, we're just going to label this thing the terminal state.
Okay.
And actually the way you can include this in the standard MDP is you just have some state that loops back to itself with zero reward forever.
Right.
And then you don't even need to worry about the terminal state. The only advantage of having a terminal state in our setup is that it gives us a well-defined point at which to update the value function. Otherwise, when do you do it? So to evaluate a particular state S, there are actually two different variants, slightly subtle different variants of Monte Carlo policy evaluation. So we want to do policy evaluation. We want to evaluate the goodness of this state S. How much reward are we going to get from state S? So what we're going to do is, in this variant, we're going to say the very first time that state S is visited in an episode, we're going to increment some counter. We're going to say, okay, well now we've visited this thing 4 times rather than 3 times. And we're also going to increment the total return. So we're going to count both two things. We're going to count over all the episodes we've seen, how many times has that, so we're going to count the times that this was visited. So there might be some episodes where this state wasn't visited at all. But if it is visited in an episode, the very first time it's visited, we update the counter and we update the total return. So we add on that particular return. And then the value is just estimated by S divided by N. I mean, this is just, basic estimating mean. I'm not saying anything fancy here. Okay. But the whole point here is that by the law of large numbers, this thing really does converge on the true value function. So the more episodes we see, the closer and closer this empirical mean will get to the expected return. So this is a very valid estimator. It's an unbiased estimator, and will converge quite rapidly on the true value function for this policy path. So all we need to do is basically look at these episodes, count how much reward you got from that first time you saw state S onwards, and now we're going to estimate the goodness of that state by averaging over those scores that you got from state S onwards. Is that clear? Okay. There's a slight variant, which is also just as valid and has the same properties, which is to say that you might have some loops. You might have your MVP might loop back round. You might see it state S more than once in an episode. So now in this case, we can say you can choose between the first visit and the every visit. So this flavor basically says every single time you visit that state, we're going to update our counter, and we're going to increment the total return. So the difference in this variant is that if we visit a state 10 times in one episode, we'll increment our counter 10 times, and we'll include basically all of the returns that we got from that state onwards in our estimates. So it might be that the first time we visited that state, we got 100 reward afterwards. The second time we visited, we got the remaining 50 reward afterwards. And the third time, there was only 10 left after that because we were almost at the end of the episode. And then you might have something where we sort of come round to the same state various times. And the final time, there's only a tiny bit of reward left. You only get 3 reward left by the time you get to here. So this is some rat moving through some maze. Comes back through the state 3 times. First time it gets 3. So the first time it gets maybe 100. Second time it gets 20. And last time it gets 3. And we're going to include all of those in our mean. We're going to take the mean of all of those things. Okay. And again, this, by the law of large numbers, actually converges on the true value function. Okay. So let's take a simple example just to maybe make this a bit more concrete. So let's say you want to make money in the casino. Can you use this algorithm to make you money in the casino? This is a nice thing to know if you can do it. So we can actually try and play blackjack using Monte Carlo. And we'll start off with policy evaluation in this lecture. And next lecture we'll actually find out the optimal way to play blackjack. Okay? So the way we're going to represent the state in the game of blackjack is by the sum of your two cards. So basically, does everyone know how to play blackjack? Okay, no, good. So blackjack, basically, you get two cards. The dealer also gets two cards, but one of the dealer's cards is showing. And the idea is that your two cards, do I have a picture of this somewhere? No. Okay. You get two cards, the dealer gets two cards, and basically you want to make sure that the score of your, you basically get to pick more cards. You can say stick or twist. You can either stay with the two cards you've got, or you can ask for another card. And then you can stick, which basically means you keep with your cards, or you can ask for another card. And basically you want to accumulate, you add up the total of all your cards, and you want to get as high as possible without going over 21. If you go over 21, you're bust. And the goal is to end up with a number, the total of your cards should be higher than the total of the dealer's cards, in which case you win. That's the game. Okay, so all that matters actually is how much our total cards are. That's our state. It doesn't matter if we've got 4 3s or a 7 and 5. They both add up to 12. So it doesn't matter how many cards we've got. The only actual relevant part of our state, the suits of the card doesn't matter. The only thing that matters is our sum. If the sum is less than 12, we're just always going to ask for another card because there's no reason not to. So the only thing we actually need to worry about is if we've got some total sum between 12 and 21. Okay? And we also care what the dealer's card is telling us. So we get some information about the dealer's state, like whether he's got, if he's got a 3, we're probably going to want to twist more. Sorry, if he's got a high number, we'll want to twist more, and if he's got a low number, we'll want to twist less. Aces, this is just a detail, but if you have an ace, it can either count as a 1 or an 11. So that's basically a piece of the state. If you've got one of these, it gives you some more choices. Okay, so you can either stick, this is turning this into an MDP now. You can either stick, which means you stop receiving any cards and you just terminate the episode at that point, or you can twist, which means you get to take another card completely randomly with no replacement. And if you stick, the reward function is going to be +1 if your sum of cards is more than the sum of the dealer's cards, 0 if you tie, and -1 if the sum of your cards is less than the sum of the dealer's cards. But if you twist, then you might go bust, which means you go over 21, in which case you just lose the game -1, and the episode terminates. Or you get 0, but it takes you on to the next step where you might choose to stick or twist again, so you don't terminate at that point. So we've turned this into an MDP, but what we don't know is the actual dynamics of this MDP. It's quite, what we don't know are things like the probabilities of the next card, which depends on stuff that we haven't seen, like the opponent's cards that are showing, and things like that. So there's actually quite a lot of, if you really wanted to work out the dynamics of this MDP, it would be quite hard to write this down, so we're just going to use Monte Carlo to estimate it very simply. Okay, are we roughly clear on what the game is? Okay, good. So, and this is what happens when we apply Monte Carlo learning to this. So this is very straightforward. We're just actually going to play according to this one strategy. Our strategy is going to be quite a simple strategy, which is just to stick if we've got 20 or 21. Otherwise, we're going to twist. This is a terrible way to play, but it's just to illustrate the game. And now we can actually look at the value function. So we've divided up the state space into basically these. So the only different variables that mattered, if you remember, were what our sum was, what the dealer's showing card was, and whether we have an ace. So whether or not we have an ace is top or bottom here, and the two axes represent our sum, and our sum is up here, and what the dealer's showing is down here. And so what we're doing is running many, many episodes. We're just going to play this strategy against the dealer thousands of times, and we're going to learn the value function. We're going to figure out what the shape of this value function is just by averaging. Basically, we're just looking at the mean score of all those episodes. And you can see it takes quite a few episodes, but after 10,000 episodes over here, we've got a pretty good idea of the shape of this surface. And after 500,000 episodes, you've probably lost a lot of money by now when you've seen it. But after 500,000 episodes, we've basically got this surface perfectly. And you can see that if you've got 20 or 21, well, this strategy is really good. But if you've got less than that, you're probably going to go bust because it's a really stupid thing to keep twisting when you've got 19 or 18, you're almost certain to get bust and go over 21. Okay, so next episode we'll see the optimal solution, but it's just to give you a flavour of how Monte Carlo learning proceeds. Okay. Now, in practice, one thing which we're going to use quite a lot is rather than computing the mean the way that we did, where you first compute the sum and you compute the total and you just divide the two together, we can do the same thing incrementally. So this is a fairly standard trick, so sorry if you've seen it before, but the standard trick goes something like this. That if you know what the mean, so basically, so this is just the definition of mean in the first line. This is for some arbitrary sum of variables, xj. And what we can do is we can divide that up into the first part, the first element of the mean, and the rest on the second line here. And that rest is itself k minus 1 times the mean for the previous step, all the time steps up to k minus 1. Sorry, I should have said we divide up into the last element and all of the elements up to that last one. And now, if we just rearrange this, rearrange it in the following way, to give us just the fact that this is equal to, so the mean that the new mean is equal to the old mean plus 1 over k times the difference between our new element and our old mean. So in other words, this is like an error term. We're basically saying, if our new thing, we want to update the mean, if our new thing is more than the old mean, we want to move our mean estimate a little bit up. And if our new element is below what we thought the mean was before, we're going to move our estimate a little bit down. And this is just a standard way to compute the mean incrementally. So how would we do that with Monte Carlo? Well, we're going to see one new episode, and we're just going to update our value function using this incremental mean. So we're going to update the counter, just the way we did before. Now we're going to update the value function using our incremental mean computation. So we've just got this term here, where we're now just looking at this error term, which is the difference between the return that we actually observed and our previous estimate of the mean. And that gives us a new estimate of the mean, based on our last piece, our latest return, our latest episode. Okay, so, but often we might not choose to actually use this particular form. In particular, if the world is changing, if we're in a non-stationary environment, we don't want to remember everything. The world is changing, so it's often very practical to actually throw information away. You don't want to take the mean all the way back to infinity, because infinity was a long time ago and the world was different then. So in practice, it's often useful to have a non-stationary estimate of the mean. And one very simple way to do that is to basically, this is sort of the standard trick where you replace this 1 over n, which gives you the sort of perfect estimate for the mean based on everything, to just a fixed step size alpha. And this is actually a way to, so what this actually means, it still takes the same form. We're going to move a little bit in the direction of the error. So if our return was more than we predicted, we'll move our value function a little bit up. If our return was less than we predicted, we'll move our value function a little bit down. But now what's happening is we're actually paying more attention to things that happened recently, instead of decaying by 1 over n. So you can think of the sort of perfect mean estimator as something that decays this step size with a 1 over n schedule, whereas we're choosing to keep the step size constant here, and that basically means we place more emphasis on the things that have happened recently than we would under this decaying schedule. So it gives us this sort of exponential forgetting factor. So it takes more account of the recent things than the old things. And essentially, this step sizes get multiplied up. You get alpha's the end with n steps back. Okay. So the reason I've kind of taken us through this is that a lot of the techniques we're going to look at are actually going to take this form from now on. So they're all going to have this form where we start off with some value function estimate, and then we're going to move a little bit, this step size, in the direction of some error term. And here the error term is between the return, how much reward we actually got in the whole episode, and our current estimate. But we're now going to play it out with this return and use different targets to move the value function towards. Okay, so is everyone clear on Monte Carlo learning? Any questions? Anyone wondering why it's called Monte Carlo learning? Turns out it was actually from the Manhattan Project, that when the nuclear bomb was being developed, there was sort of a code name for some of the theory that was used there, and they were looking into these sort of random trajectories that were being followed by to estimate what would happen to atoms, and so they had this code name of Monte Carlo for this this project, and it sort of stuck around, and now here we have it in reinforcement learning. So at Monte Carlo, across machine learning typically means this estimation, sample-based estimation of some value rather than looking at integrating over a whole space. You use some sample.
And there was also the name of a casino, Monte Carlo.
Well, it is now.
Huh?
So Monte Carlo is the place where the big casinos are.
No, so I think it's also, in fact, it was the name of casino that one of the person who's working for the Manhattan project. He had a uncle who was keep going to that Monte Carlo casino anyways. So.
Okay. Well, I didn't know that. Right. So we're now going to move on to our second sort of class of methods to solve the same problem. So we're still interested in methods that learn directly from episodes of experience, so just like Monte Carlo. And again, this is another model-free method, so again, we don't require or assume any knowledge of the MDP transitions or the rewards. But what's different about TD is that it can learn from incomplete episodes. So we don't need to wait all the way until we've seen a complete episode. And the way we're going to do that is by bootstrapping. I'll explain what bootstrapping means in a minute. Essentially it means learning a guess from a guess. So we're going to update the value function a little bit towards a guess of what the value function should be. So you start off with some estimate of the value function, and you move your estimate towards another estimate of the value function. That's what bootstrapping is. Okay. And one nice thing about this is that because it learns from incomplete episodes, we can use TD methods in MDPs that go on forever, continuing MDPs, which we'll see shortly. Okay, so again, we're trying to learn VPI. We're doing policy evaluation, and next lecture we'll extend that. And we're going to take these some experience, so scale function and reward tuples under our policy, which might be uniform random. We're just trying to figure out how good it is. So before we had our Monte Carlo method, and just as I was just saying, this is essentially where we start with our value function, we move it a little bit towards the actual return. So the error was between the actual return and the value function. Now what we're going to do is we're going to look at the simplest temporal difference learning algorithm, which is an algorithm called TD0. And we'll start to see a few of these as we go on. But the idea of TD is instead of moving the value towards the actual return, we move it towards the estimated return. So what we're going to do is we're going to look one step ahead, just as we did with dynamic programming. We're going to look one step ahead. We'll say if we look one step ahead, we'll get one step of reward, and we'll get the value function discounted of the state that we ended up in. But unlike dynamic programming, we're just taking one sample. We're not doing like a full look ahead. We don't even know the dynamics of the MDP to do a full look ahead. So we're taking one sample. We're saying, okay, I was in some state. I took a sample. I actually got some reward, RT plus 1, and I actually ended up in some state, ST plus 1. This is the sample reward and sample state. We're going to use those as our target. So the target we're going to move towards is this estimated return. And now we're going to update the value in just the same way. So if our estimated return is more than our value function that we predicted, we increase our value function. If it's less than we predicted, we decrease our value function. We have some step size here that determines how rapidly we move towards it. So it's a very straightforward idea.
So,
Yeah.
so essentially you do backtracking of the VST. Because when you go to VST plus 1 to take your sample, you must also go to VST plus 2
Yes.
to take the sample for that sample. And
So there's no backtracking. So basically, all you need to do is when you sort of need to. So just as in Monte Carlo, it's like you need to have in your hand in order to be able to do an update. You need to have in your hand the state that you started from and the return you got right at the end of the episode. Whereas for TD, all you need in your hand is all the algorithm needs in its memory, if you like, is the current step and the next step. So it needs to remember that it was in this state and it moved to this state. And now it's got enough information to update where it came from towards where it ended up. And then it moves on to the next step, and then it moves on to the next step, and then it moves on to the next step. So it doesn't do any backtracking, it just has to remember that it was in this state and it ended up in this new state. Okay, we're going to call this thing the TD target. So this thing that we're moving towards, this reward plus estimated value from the next state. Okay. And we're going to call this error between them, the TD error. So the difference between the TD target and what we thought we were going to get is the TD error. So this, we basically update the value function a little bit in the direction of the TD error. Okay, so here's an example to try and make this a bit more concrete. So this is from the Sutton and Bartow book. The idea is basically that you're driving along on your way to work, and you're trying to come up with some estimate of how much time it's going to take you to get to get back. Actually, you're leaving work and trying to get home. And so when you start off, you sort of estimate, well, I'm leaving the office. I have some prediction. This is like your value function you start with. I'm going to predict that it's going to take me 30 minutes to get home. But then it takes you 5 minutes to get out of the office, and by the time you get out of the office, you notice that it's raining. So you're in some new state, and based on that new state that you found yourself in, you're going to say, well, actually from this state, I now predict that it's going to take me longer. It's raining. I'm going to predict it's going to take 35 minutes from now on because it's raining. And then you go onto the motorway or the highway if you're American, and you now sort of go along quite smoothly, everything's consistent with what you predicted, but just as you are sort of leaving this motorway, you get stuck behind a truck, and so that bumps up your prediction of how long it's going to take you by another 5 minutes from what you had thought, and then you start to get closer to home, and eventually you end up home. So as you go along, your predictions are varying based on what's happened to you. The agent starts off in some start state, but as it moves along, it takes this random trajectory, and it finds itself in unexpected situations, and those unexpected situations can have predictions which are more or less than what it originally thought it would have. So what would happen with Monte Carlo and TD in this situation? So in Monte Carlo, what would happen would be, you start off with your prediction, say from leaving the office, you'd start off saying, well, I thought there was, I had a prediction that it's going to take me 30 minutes, but in the end, it actually took me 43 minutes to get home. So you'd update that 30 a little bit towards 43. Whereas in TD, we do something different. We update immediately after the next step. We say, I started off predicting it was 30, but then I went outside and I saw that it was raining, so my prediction is now this 5 plus 35, so I'm going to update this 30 a little bit towards the 40. So if we actually look at what happens along this trajectory, we end up with very different changes recommended by either the Monte Carlo approach or the TD approach. Now here we're assuming a step size of 1, you move all the way to the prediction just to make it clear what's going on. So here you can see the actual outcome was 43, so we update every single state that we took along this trajectory, we update all of those states towards that 43. We basically think, oh, it should have been, all our predictions should have been 43 essentially. Total travel time should have been 43 from all of those states. Whereas with TD, we just look this one step ahead and we base what our prediction should have been on what happened to us next. We look one step ahead and we say, I thought I was in this situation, then something happened, and I revised my predictions based on what happened. So we update what I thought towards what I realized after doing something. Okay. So which is better? Well, there's advantages and disadvantages to both. There's some big advantages to TD. It can learn before knowing the final outcome. It doesn't need to wait all the way to the end of the episode. So it can learn online after every step, whereas Monte Carlo has to wait all the way to the end of the episode to see this return. And TD can even learn without the final outcome. So this means that if you only have an incomplete sequence, if you have some agent and it's wandering around its world and then it just, the robot breaks or whatever it is, it can still learn from that incomplete sequence. It doesn't need to wait until it reaches the end of the episode. Whereas Monte Carlo can only learn from complete sequences. And as a result, TD can work in continuing, non-terminating environments. One thing to add to that, this is some recent work we had, was actually this becomes even more important, the difference between these, if you actually deal with some concurrent applications, like sort of many internet reinforcement learning examples. You have like a load of users who are operating online at the same time. And actually, it becomes even more important to bootstrap in that situation. Because if you're always waiting until you wait to see what the user does, and you have to wait maybe 3 months to see whether they buy your product or not, then in that 3 months, there's this enormous opportunity lost. You haven't learned, so you show them something stupid that's really going to offend them. And then you wait 3 months to learn from that. And now in the intervening time, for all of that 3 months, you're still showing the same stupid, offensive content to all these other users by mistake, because you haven't learned that it's a bad idea yet. Whereas if you bootstrap, you can learn straight away. You can learn that you ended up in a situation where you now predict they're going to be upset. So you can apply that straight away to all your other customers. That's just one concrete example we've had recently. Okay. So there are many reasons to choose to use TD. What we'll actually see is there's also efficiency reasons later on to use TD rather than Monte Carlo. And the reason is basically down to a bias variance trade-off. So when you use the return, when you use Monte Carlo learning, you get this unbiased estimate of the value function. So what do we mean by unbiased? Well, we basically mean that if you take the expectation of this return, it is to be pi. Whereas the TD target, if you take the expectation of the TD target, it's not necessarily equal to v pi unless that vst plus 1 is itself the true value function. So it's a biased estimate of v pi. But the TD target is much lower variance. And sort of the reason it's lower variance is that if you think about it, the Monte Carlo estimate has to wait for this complete return to happen. There's all kinds of random events that happen to get all the way to the end of this return. You've got your robot, and maybe for 1,000 steps, it's going to sort of wander around in this environment. Things could happen to it. It can take random actions. It can see random rewards. It's going to be moved into random states. So there's a lot of randomness inherent in that whole trajectory. And by the time you get to the end of that whole trajectory, there's a lot of noise there. You've accumulated a lot of noise. And so it can be very slow to learn by Monte Carlo because you have to sort of average out all of that noise. Whereas the TD target only depends on one random action, transition, and reward. We're only looking one step ahead, remember, to get this TD target. So to get this RT plus 1, that's gamma VST plus 1, we're only looking at what happened for that one action, that one transition, one reward. Okay, so let's think again about the advantages and disadvantages. So Monte Carlo, high variance, zero bias. As a result, it's a very nice algorithm in terms of its convergence. It's an unbiased algorithm. We know how these algorithms work. It was going to converge to the true value function. Even if you throw in function approximation, this thing still works. It's like standard. It's just like supervised learning. Basically, Monte Carlo is just like supervised learning. You're learning what the value function is from example returns. It's also not that sensitive to the initial value. It's going to converge regardless. It's very simple to understand. I mean, it's just taking the mean. I mean, everyone understands the mean. Okay. Whereas TD is much lower variance, so it can be much more efficient, but it introduces some bias. So we should be wondering, well, is it okay to introduce that bias? Does it still work? So it's usually much more efficient than Monte Carlo, and the good news is that it still converges. It still converges to the true value function. So I'm not going to show the proof, but it's well known that TD0 and the variance that we're going to look at later on in this class do all converge to the true value function. So even though there's bias, that bias sort of gets cancelled out over time. It gets less, it gets reduced. And sort of the intuition is that basically, so this line here that says unless we've really reached the true value function, so you kind of just need to know that you're making progress towards the true value function in your target. So if the target's getting closer, then if you imagine that you're just propagating this information backwards from the end, it's sort of clearer that each step you're making some progress in making your value function better, and therefore your predecessor is going to make a better estimate. Okay, so.
If alpha is not small enough, you always oscillate. Is that true? If alpha, the update step.
So, okay, so the convergence properties, this is like standard sort of stochastic approximation theory, so this assumes that you use like Robbins-Monroe step sizes where you decay the step size like 1 over n.
Okay, so alpha is not fixed.
Alpha is not fixed if you really want convergence. Yeah. Otherwise, you will always oscillate a little bit. That's true. Okay. But even with fixed step size, you can actually show that it will oscillate around the correct solution. Mm-hmm. So you basically get within some tolerance of the true solution. So it's like you actually get like a differential equation that sort of tracks. Mm-hmm. You get this sort of trajectory that tracks the true solution, basically. Anyway, that's all for detail. Mm-hmm. Okay. So TD converges, but what we'll see in the second half of the lecture course is that it becomes a bit trickier once we introduce function approximation. That because we've introduced bias, that TD actually doesn't always have the nice properties we want once we introduce function approximation. We can't just do things like gradient descent that we do from in supervised learning literature and expect it to work perfectly. So there are some issues there that we'll need to address. It's also a bit more sensitive to the initial values because with bootstrapping, we're updating our guess from a guess. If our initial guess is wildly wrong, it can sort of throw us off for quite a while before we recover. But despite all those caveats, TD can be often dramatically more efficient. So if given any given problem, it's quite likely that TD will work much more efficiently in real-world problems, as we've got evidence that this is the case across a wide variety of problems. So here's one very simple example to give you a flavor of the difference between the algorithms. It's a very trivial example. It's a random walk. So there's these 5 states, A to E, and this agent's just going to walk randomly, so it's 50% chance it moves left, 50% chance it moves right. If it gets all the way to the right-hand side, over here, it's going to get a reward of 1. For all other transitions, it's going to get a reward of 0. If it gets all the way to the left, it's also going to terminate. Okay, these squares basically represent terminal states. So there's some true value function. We know what this true value function is. It's actually this straight line. If you solve it, this straight line going up there in this sort of thing. Great. That's the true value function for states A, B, C, D, and E. And this is the value going up this y-axis here. And what we see here is that if you initialize the value function to 0, that's the flat line right in the middle, then this is basically showing what happens if we run our algorithm. So this running TD algorithm, the TD0 algorithm, for the first 10 steps. This is using a step size of 0.1. And if you run it for 10 steps, then you get this blue line where it's kind of moved correctly in the sort of right direction. After 100 steps, it's almost tracking the right solution, and so forth. It converges very quickly on the true values. So if we actually compare now Monte Carlo with TD learning, so this is all for just fixed step sizes, so no decaying of the step size here. But for different fixed step sizes, this is the comparison of how TD and Monte Carlo are doing, and this is the root mean squared error averaged over all 5 of those states. So we're basically looking at how well it predicts the value function in the states A to E. What you see is that TD basically reduces the error much more rapidly across a wide variety of step sizes than Monte Carlo learning. So that's the effect of bootstrapping. This is what happens. This is that bias variance trade-off. It's really able to very quickly reduce the noise in this problem.
And C has only one curve for different alphas?
Sorry, I should explain. So the black lines are Monte Carlo with different step sizes, and the grey lines, these 3 grey lines down here are TD with 3 different step sizes.
Okay.
So in this case, the TD dominates Monte Carlo in this example. That's not always so clear cut. Okay. So we've seen that both of these algorithms converge. They have the nice property that as the number of episodes or tuples of state action reward experience increases until we've got infinite amounts of experience, these estimates of the value function will converge on the true value function, v pi. This was our goal policy evaluation. But here's a question. What happens if we have only seen some fixed number of episodes? So we've seen k episodes, and now we're going to stop after k episodes, and we're going to say, okay, what's the best solution you could get from those k episodes of experience? So before we were doing things kind of online, it was like each time we saw something new, we're updating our estimate a little bit. Whereas here we're asking for the batch solution. So we're going to stop and we're going to say, okay, if you go over that experience again and again and again, what solution will you find? So we're going to repeatedly kind of sample an episode pick out one of our k episodes, and we're going to rerun that episode. We're going to apply one of our algorithms, either Monte Carlo or TD0, to that episode. Okay, so let's actually run through a concrete example and see if we can figure out what's going to happen. So here's the problem we're going to look at. It's called the AB problem. There's 2 states here. There's no discounting. There's 8 episodes of experience, and the 8 episodes are very simple. The first episode, we start in state A, we get 0 reward. We move to state B, and we get 0 reward. Okay? The second episode, we start in state B, and we get a reward of 1. And the same for the next episodes, all the way down to this final episode here, where we start in B, and then we get a reward of 0. And the question is, what's the value function for A, and what's the value function for B? Okay. So let's do B first. So, any volunteers? What's the value function for B after this experience?
3/4.
Right. Okay. Now here's the more interesting one. What's the value function for A? So 3/4, I mean, just there were 6 episodes in which we got 1 and 8 episodes in total. Okay. So what's the value function of A?
Because we are assuming the initial estimate is still 0. Right? We are assuming the initial estimate for it to be 0.
I'm letting you use whatever algorithm you want. I'm just asking you, as a human, what do you think the value is?
As a human.
Don't worry about which algorithm you apply. What do you think the value is, having seen this experience?
0.
0?
Yeah.
3/4.
3/4. Okay. So let's have a show of hands. Who thinks it's 0? Who thinks it's 3/4? Okay, so that's good. It's about half and half. So, so it turns out you're both right. That these are the 2 different solutions which are found by Monte Carlo and TD learning. Okay, so let's see, for those of you who've thought of it the one way, it might be hard to see it the other way. So let's just run through those 2 different ways of thinking about the problem. So I guess, so one way to think of this is that it's just as we did with state B, that we can ask the question, you know, every time we started in state A, we got how much total return did we get? That's what Monte Carlo would do. So when we started in A at the top there, we ended up with a total return of 0. So the only episode in which we actually saw A, we ended up with a return of 0. So it's fairly logical to say that therefore the value of A is 0. That's what Monte Carlo does. It looks at complete returns. But it's also logical to do this, which is to try and estimate what the MDP looks like from the data. If you were to estimate the MDP, you would say, okay, well I started in A, and every time I started in A, I transitioned to B 100% of the time with 0 reward. And when I was in B, 3/4 of the time I got a reward of 1, and 1/4 of the time I got a reward of 0. So if you now try and look at this MDP and solve this MDP, well, if you were to solve this MDP, you'd end up with the estimate of 3/4 now. But every time you start in A, you end up in state B, and we knew that the value of state B was 3/4. So they're both perfectly reasonable, consistent estimates that think about the problem in different ways. So what can we say about these things? Well, Monte Carlo and TD find different solutions with different properties. What Monte Carlo finds is the solution with the minimum mean squared error. So it looks at the mean squared error between the value function and the actual returns, and it minimizes that mean squared error. So it's the best fit to the observed returns. So this is just looking at the mean squared error between the returns over all steps and all episodes. That's what those 2 sums are over. So in the AB example, that's how we got our value of A being 0. Whereas TD0 finds something different. It finds, basically what it converges to is the other thing we looked at. It finds basically the best fit, the MDP that best explains the data. So it's going to form a Markov model. It's going to, implicitly, it's estimating the transitions of some MDP and solving for that MDP, even though it never ever explicitly estimates that thing. That's the solution it finds. So it's equivalent to finding the MDP that best fits the data. Don't worry too much about the math, but it's basically just finding the MDP that best fits the data and then solving for that MDP. Okay. So in the AB example, that was 0.75. Right. So just to hammer home again then this advantages and disadvantages. Another way to put this is that TD, the reason it's more efficient is that it exploits the Markov property. So if we look at this example here, Monte Carlo was inefficient in this example because it wasn't able to notice that it wasn't able to reuse these final 7 episodes of data there. They were basically thrown away. And the only way that TD was able to exploit these was by assuming that the Markov property actually holds in this problem. So if you assume the Markov property holds, well then you can say, well okay, if there was a Markov model, then what I've learned about B must also be true when I start from A. So TD exploits the Markov property, and so if you're really in a Markov environment, if you're really in an MDP, then TD is typically going to work much better. Whereas Monte Carlo doesn't exploit the Markov property. And what that means is that if you're in a non-Markov environment, where the Markov property doesn't actually hold, where it's just an approximation, then Monte Carlo can be much better. Okay. So this is just kind of, these 3 slides are kind of just to give you an overview of where we're up to. So this is like just a recapitulation. So imagine you're in some world, and we're now kind of doing some look ahead from, you're at time step little t here, starting at state st, and there's this big tree of possible things that could happen to the agent from here on. And so here we're representing the whole tree of possibilities. These capital T's here represent terminal states in this sort of look ahead tree. So it could move ahead. The black dots are like actions we could take, and the white circles are states that we might end up in according to the environment. So there's this big look ahead tree of possibilities. And what we've looked at is Monte Carlo, which basically takes this sort of whole sample trajectory. It samples this all the way down one complete path, and it updates the value function of this root state based on this single sample trajectory. So it doesn't have to do a brute force look ahead, it's just sampling a trajectory moving towards that. Whereas TD is just looking one step ahead here. It's moving one step ahead, and it's updating the value function at the root towards what would happen if you looked just one step ahead, sampled one step ahead. Okay. And what we looked at last lecture was dynamic programming, which, like TD, was also looking one step ahead, but in a brute force way. So if you know the dynamics of the environment, you can ask the question, well, what's all the different things the environment could have done under all the different ways that we might have picked actions? So that's what dynamic programming was doing when we did things like iterative policy evaluation. Okay. And there's also, one more extreme possibility, which is we could do something like dynamic programming, but looking all the way to the end of the search tree, and we call that exhaustive search. If we really just tried to brute force enumerate this entire search tree, look ahead all the way to the bottom of the search tree, and evaluate everything all the way down to the leaves. That's what exhaustive search does. So we're going to kind of put these things together a little bit and try and look at the dimensions of what varies between these different algorithms. So the one important dimension is whether they bootstrap or not. So bootstrapping is whether the update involves an estimate, whether we're moving towards our estimated next value, or we're looking all the way to the sort of real return. So Monte Carlo doesn't bootstrap. Dynamic programming does bootstrap. If we look at this, we're looking one step ahead. But now if we want to estimate the value of st plus 1, well, we have to have some estimate of that value function. This was dynamic programming. We're moving a guess towards a guess because we're moving our value function at one iteration towards the value function we had at the previous iteration. So dynamic programming bootstraps and TD bootstraps. The other important dimension is whether we're sampling the expectation or whether we're computing that expectation by integrating over all the possible things that could happen in our policy and in the environment. So Monte Carlo samples. It just samples one trajectory down this tree, look ahead. Dynamic programming doesn't sample, it does full width, look ahead, and TD samples. So if we put that together into a picture, we end up with this picture here, where we've got two dimensions of the sort of space of model-free reinforcement learning. Just the space of reinforcement learning, they're not all model-free. The space of reinforcement learning algorithms that we've looked at so far. So we've got this dimension here, where we can move from dynamic programming at the top, which does full backups, that's the complete expectation, versus these ones that sample down the bottom, which are temporal difference learning and Monte Carlo. And then in this dimension, we have whether or not we bootstrap. So over here, we don't bootstrap, we look all the way to the bottom of the search tree. Over here, we look just one step ahead. And now, the question we're going to ask is, are there algorithms that live in the middle of this diagram? Is this the complete space? Do we only have to think about the corners, or are there things that live in the middle? And what we're going to see is that there's a whole space of algorithms in the middle here. So what we're going to concentrate on for the rest of this lecture are things that move between these one-step look ahead and infinite look ahead. We won't concentrate so much on the other diagram, but it's straightforward to imagine that you don't have to just sample one thing. You could, let's say sample two possibilities at each step. So there is a spectrum that lives on this other dimension as well. We're not going to look there so much. Sparse sampling methods would be an example of this approach. Okay, so I'm just going to pause there for a second before we move on to the last chunk. So any questions about what we've seen so far? Monte Carlo learning, TD learning, this sort of space of possibilities. So what I want you to have in your mind is actually that they're all trying to compute the same thing. I mean, all of these algorithms are trying to figure out v pi in one way or another. And really what's happening is they're all based on, you can think of this tree as multiple expansions of the Bellman equation. The Bellman equation is looking one step ahead. You can iterate that thing. And TD is like a sample-based approach to solving it. Dynamic programming is a full-width approach to solving it. Okay. So, TD lambda is the spectrum between these TD methods that look one step ahead and Monte Carlo methods that look infinitely far ahead. So let's understand how that works now. TD lambda is probably the best known reinforcement learning algorithm, very widely used. Okay. So, we're going to consider the following idea. If we go back to this picture here, so to hammer it home again, when we had Monte Carlo, we looked all the way to the end, and then we used complete return from the end as our target. When we use TD0, we look just one step ahead. But clearly, I mean, it's reasonable to look 2 steps ahead or 3 steps ahead. And then if we look 3 steps ahead, if we look 2 steps ahead, for example, we might reach this state here, and then we would say, okay, well, let's update our estimate towards the reward we got at t plus 1, plus the reward we got at t plus 2, plus the value function at st plus 2. And we can do that for any number of steps ahead. So that's what we're going to do now. We're going to do n-step TD targets. So we're going to look n steps into the future. So these are examples of sort of what our look ahead would look like. These are our backup diagrams again. We might look 3 steps into the future here. We're going to look 3 steps and we're going to use estimate the value function at the end here, and we're going to update our estimate towards 3 steps of reward plus the value function at that time at the end there. And Monte Carlo is just the extreme where it goes to infinity. Okay, so specifically that gives us these n-step returns. So the 1-step return at the top there is exactly our TD0 target that we were using, the TD target, where we look ahead 1 step, we get the reward at time t plus 1, plus the discounted value function at the state you end up in. So you're in some state, you move ahead, you get the reward for 1 step, you get the value of where you ended up, we're going to add those things together, that's our target, that's how good we think. After that 1 step of experience, that's how good we think, that's our revised estimate of how much reward we'll get. We can do the same thing now. The 2-step return, we could equally use this as our target. We could say, okay, we'll look rt plus 1 plus gamma rt plus 2, we're discounting, plus gamma squared, discounting twice the value function and where you end up at time st plus 2. And so forth, all the way down to Monte Carlo, which just does this infinitely far ahead. And by the way, if you go infinitely far ahead, the value function at the terminal state is always defined to be 0, so you end up with this. Intuitively, if the episode terminates, there's no more reward you can get, so the value function is just 0.
Would you update the value of the step you moved to as well? It's
No.
like you have that information right, and you've got that information at hand. Why wouldn't you?
The reason you wouldn't, so if you've just seen one transition, so let's say you've just seen one transition, you were in some state, you've moved to some new state, maybe 1 step ahead or maybe 10 steps ahead. So now you've got a revised estimate of the value 10 steps ahead because you've seen some reward along the way and you've got a better estimate of what the value function would be after you've taken those 10 steps. So you can upscale this guy, but you haven't got a revised estimate of what the value of this guy is because you haven't seen any new information from there.
But then all the intermediate steps between the one you ended up at and the one you began at, all those ones you have rewards, right? You've got rewards, you're not.
Okay, we will see this in subsequent lectures. The only way you can do that is if you generalize. So if we're just doing table lookup like we are at the moment, where every state has its own value function, so sorry, its own value. So there's one value for each state. Now, if you're looking back retrospectively, so this is a really good question. So if you're looking back retrospectively, so let's take a really simple MDP like this, just to make, in this example, it's going to be really clear, okay? So you've moved from here to here, you've moved from here to here, you've moved from here to here, and now you've ended up with R1 plus, let's make it undiscounted, plus R2, plus R3, plus our value function here, which we're going to estimate. Let's say our value function just started off as 1 here, plus 1. We started off estimating this was going to be 1, and so we had our V of SA, and our V of SB, and now we're going to update this thing towards this thing, okay? And now let's say all of these rewards were 1 as well. Okay, so now we're able to say, well, I started off thinking the value was going to be 1, but I actually got 1, 2, 3, so 1 reward, 2 rewards, 3 rewards, and I ended up in a state with a value of 1. So we're going to update this towards 4. Okay, so we're going to update our 1 a little bit towards 4. But the question is, can you update this 1 towards anything? And the answer is you can't, because you don't know what's going to happen to the agent after this.
But what about the 2 nodes in between, like the ones you transition to? Can you not update those to value of 3?
Yeah, so the idea of the end step TD is going to be that all of these get updated as well. So this one's going to get updated to there, this one's going to get updated to there, this one's going to get updated to there, and so forth if we continue this. So they're all going to be updated. And in the TD0 case, that's simpler because it basically means that you just get this chain of updates that looks like this. So every time you take a step, you update the value where you came from towards the value where you got to. Sorry, I thought you were asking something different. Okay. In fact, you can do something a little bit more like what I thought, but only in as much as you can generalize. So if you want to know, well, what's the value of this state, can you update the value of this guy just from what you've seen before? Well, you can if you think that the value of this state tells you something about the value of this state. So if you've been through things and you think that what you've been through can generalize to where you are now, then you can do that. But that's a bit more later lectures about. Okay, so we're doing end-step returns. So we're basically doing this thing where we're going to update every value a little bit towards these targets. So we've got this end-step return, Vn. This is the thing that looks n steps ahead. And now we can do n-step temporal difference learning, which is exactly this thing here. So here we've got like 3-step temporal difference learning, where we're looking 3 steps ahead. We're updating the value here by the reward plus the value at the end of that. So that's 3-step temporal difference learning. We can define that for any n. Okay, so let's do a random walk again. This is a larger random walk. I think it's 21 states in this random walk. And this is what happens for different n. So this is just, I mean, it doesn't matter if you look at the top or the bottom. That's about whether you do this online or offline. That's kind of a detail. But in either case, what you see is that the performance of the algorithm varies quite dramatically based on n. Like if you know just the right number of steps to look ahead, then you'll do a lot better than if you just were to do TD0 or just to do Monte Carlo. And so what you see is that as you move to the top left here, we're getting closer and closer to Monte Carlo. There's a lot of performance that you can gain by moving away from Monte Carlo and bootstrapping, but at some point you sort of you do worse again. And actually TD0 is a little bit better than Monte Carlo, but these intermediate values of n can do much, much better again. So what we'd like to do is have a robust algorithm which is able to sort of not know in advance exactly what n should be, but just sort of get something from all of those different possible n's that could be useful. So that's what we're going to do. That's what TD lambda does. It basically averages over all of these different n-step returns. Okay, so let's consider a simple case. Let's imagine that we wanted to average 2 different n-step returns. Let's say we've got like a 2-step return here, and we've got a 4-step return here. And let's say we want to kind of have one backup. We're going to move our value function towards one target. But the target we're going to say is we can take half of the 2-step target and half of the 4-step target. Well, we can just do that. We can just average together the V2 and V4, these returns that we defined before, and give them a weight of a half and a half, say. And that's a perfectly legitimate target to move towards. So we can now update our value function towards this target here, this combined thing here, which is basically combining information from 2 different sort of timescales together. We're looking ahead 2 steps, and we're looking ahead 4 steps, and we're just combining together this information we picked up from different look-ahead magnitudes. So now what we're going to do is basically use the same idea, but we want to efficiently, with an efficient online algorithm, combine information from all different time steps that we could look ahead. So that's what TD lambda does. And the way it does it is it has basically this geometric drop-off in the weights that are used. So here we had half and half. We were weighting these things equally. What TD lambda says is it basically says, okay, the 1-step return, this is what was used in TD0, it's going to be weighted by 1 minus lambda for some parameter lambda. The 2-step return, we're going to multiply that by lambda. So lambda is a number less than 1, between 0 and 1. So this is smaller now. We're giving this one a smaller weight. This one is going to be multiplied by lambda again. It's going to get a smaller weight, all the way down to the end. And so we're getting smaller and smaller weights as we look further into the future, and we're decaying the amount of weight we put on each one by lambda at each step. And then what we're going to do is we're going to average all of these things together. So now we've got weights for each of these returns all the way to infinity. And if you add them up, all of these weights sum to 1. It's just the geometric sum. Okay. So specifically, we're going to use the weight 1 minus lambda, lambda or lambda squared or lambda to the n in general. And we're just going to take the lambda return. So now this is this thing here, v superscript lambda, means rather than looking one particular number of steps ahead, we're averaging over all of the n-step returns. So this is now the lambda return. We're averaging over all these lambda returns. We're averaging over all these n-step returns. So just like here, where we're doing half and half, we're now averaging over all of the possible look-aheads we could use for all n up to infinity, and we're just weighting them by this lambda value that gets smaller and smaller and smaller. And so now we have our first TD lambda algorithm. This is called the forward view TD lambda algorithm, where all we do here is just as before, we're going to update our value function a little bit in the direction of our lambda return. So this lambda return is our target. We're averaging together what the one-step return tells us, the two-step returns, and three-step returns. We're going to average them all together into one target. We're going to move our value function a little bit towards that. So a little bit towards what all of these things are telling us to do. Okay. So this is the weighting function. This is what it looks like. So this is the exponential drop-off. We started off with 1 minus lambda for the first step here, and then it just decays by lambda every single step. So this colored in hatched column here is the weight that's given to one of the returns in particular, say the three-step return. And every single step, the weight that's given to that target, to that n-step return, is decayed by lambda. And then if you actually terminate in some episode, then all the remaining weight is assigned to the final return.
So, but n-step return requires you to take n steps.
Yeah.
So, but then, so if you're averaging over from n equals 1 to infinity.
Then you have to go all the way to the end of the episode to do that.
Right, right.
Yeah. Good.
No, but so for any lambda, you'll have to wait until the end of the episode.
Yes.
Okay.
Yeah.
Okay.
So, next slide, I think. After this. Wait one more slide. Hold that thought. Okay. So, in fact, maybe it's even this slide. So, this algorithm is called forward view for a good reason. That actually we're having to look forward into the future. So, we're updating the value function towards the lambda return. So it's like we're looking ahead to all of the different look-aheads that we could use. We're looking one step ahead. There's the agents looking one step ahead there, looking 2 steps ahead there, 3 steps ahead there. And it's looking all those steps ahead, and it's using what actually happened at those time steps, the amount of return it actually got following this one trajectory, as the update that it's going to use. So it needs to look forward to get the target that it's going to update the value function towards. So you can only do this by looking into the future. So you have to start, if you want to update the value at ST, you have to be able to look all the way to the end of the episode to compute this return, this lambda return. So it's much like Monte Carlo then, it has the same problems as Monte Carlo, but this forward view of TD lambda can only be computed from complete episodes. Okay, so we're going to fix that in just a minute. But before we do, let's go back to the random walk. So this is applying the forward view TD lambda algorithm for different lambdas. Sorry, maybe I should put these side by side, but it's a bit more robust than the in-step returns. It still matters what lambda you choose. So if lambda is set all the way to 1, what we'll see is that's equivalent to Monte Carlo. And if lambda is set all the way to 0, that's equivalent to TD. So we've still got a spectrum, but it's actually more robust in between, and you don't need to have as much knowledge about how far to look ahead with lambda. And it can do much better than any individual n-step return as well. Okay. So are people clear about what this algorithm's doing? Okay. So now we're going to move to something which solves the problem that we mentioned there. So this is what's actually used in practice, the backward view TD lambda. So the idea is that the forward view kind of provides this theoretical view of what we would like to achieve. But in practice, we do something different. We use the backward view TD lambda, which is a mechanistic version of the same algorithm, which is actually online, applied every step, can be applied to incomplete sequences. You never need to look into the future, you just need to look from one step to the next step. and that's it. You don't need to hold anything in memory, and you don't need to wait until your episode completes. Okay. So, let's go back to our rat. So our rat's sitting in a little maze, and here's 3 bells, and then the light comes on, and then it gets electrocuted. Okay. Sorry, I'm really mean to this rat. But, okay. And the question is, did the bell cause it to get electrocuted, or did the light cause it to get electrocuted? Well, we don't know. This is called the credit assignment problem. The credit assignment problem is, something good or bad happens. Which of the events that led up to that reward, were the cause of that reward? So there's some heuristics we could use to solve this credit assignment problem. One very simple heuristic would be to say, okay, well, the thing which happened most often would be the thing that caused it. So in this case, that would be like saying the bell caused the electric shock. The bell happened 3 times. Surely it was the bell that electrocuted the rat. There's another heuristic we could use, which is the recency heuristic. So if something happens really recently, we expect that that's the thing which causes it. So in this case, we'd say, well, it's obviously the light that caused the electric shock. The light just came on and then it got electrocuted, so it must be the light. Okay, so these are 2 natural heuristics. And actually, it turns out that what we're going to use is something which combines both of these heuristics together in a very natural way. We use something called eligibility traces, which combines both heuristics. And all we're going to do is basically, if you look at this diagram, imagine that imagine our bell goes off at these times here. Okay, there's some rat walking along, the bell goes off at these times. We're trying to estimate something about how much that bell is contributing to it. And all we're going to do is every time the bell goes off, we're going to sort of increase its eligibility. We're going to say, okay, this bell's happened once here, once again here, once again here, once again here. So this is like a frequency heuristic. We're counting how often the bell's gone off. But in the meanwhile, we're going to decay this eligibility trace every step by some constant factor. So we're decaying it back down. If we don't hear the bell for a while, we're going to decay it back down towards 0, and then we're going to up it again every time it happens again. And so now, if at any point we get a reward, the assumption is that the amount that this particular event, the bell, at this state, how much does the state of hearing the bell contribute to the reward? Well, if the reward happens here, we assume that it's this amount. If it happens here, we assume it's this amount, and so forth. This is the eligibility of that particular state for whatever happens next. Okay. So just in math, what we're saying here is we're going to keep some value which we can call E, and it's indexed by time here. And what we're going to do is we're going to both discount it by gamma, this is our discount factor of our MDP, and we're also going to decay it by lambda. So lambda is just going to be some number now, which is going to turn out to have exactly the same semantics as the lambda we had before. We're going to decay it by some lambda. This is like the how quickly this slope drops off here. And then this is just an indicator function here saying if S is actually equal to, if the state that we're actually in is equal to the state of this eligibility trace, then we'll increment it. That's just this counter here. That's just moving up every time we're actually in that state and ignoring it every time we're not in that state. Okay.
So bell and light will have separate eligibility.
Every state has a separate eligibility. So there's a different E for each distinct S. So it's actually an eligibility function. So yes, for the bell and the light, if you think of those as 2 different states. I know I'm using state a bit fuzzily here, but for each state there's going to be a different eligibility trace. So how much, if you're in some state in the maze and then you end up getting electrocuted, how was it because you were in this state of the maze or because you ended up in some later state of the maze? So now what we're going to do is we're going to look at the backward view of TD lambda. And the idea is we're going to use eligibility traces to construct an algorithm. So for now, just imagine this is completely heuristic, this algorithm, and then we'll show that it's not in a minute. So we're going to update the value function for every state, S. So this is different to TD0, where we only updated the one which we were in. Now we're going to update the value of every single state at every step, regardless of whether we're in it or not. And the amount we're going to update it is going to be in proportion to 2 things. So this update here, V, we're going to update V, and we're going to move it a little bit, alpha, in the direction of the TD error. So this is our normal thing. This is, so the TD error, remember, let me back up. Sorry about this. We repeated this, but I realised I didn't emphasize this. Yeah, I've gone too far. Here. So remember, this is the TD error. The TD error is the difference between our TD target, after one step, what we think we were going to get, and what we thought we were going to get before we took that step. So it's the difference between our one-step target and our current estimate of the value. That's the TD error. And basically, all of these algorithms we can think of can move a little bit in the direction of alpha, delta. That's the TD0 algorithm. We move the value function towards alpha, delta. So we move v equals v plus alpha, delta. Okay? So have that in your mind. Now we're going to look at the difference with this new algorithm, which we're inventing. Okay. And all we're doing is we're now modifying this by this eligibility trace. So we're updating every state, the value of every state, a little bit in the direction of the TD error. So we're in some state, we see some surprise where we thought the value was going to be 10, and we actually ended up in a state where the value was 20. So we're surprised, but how much does that surprise contribute to us changing our value function? Well, that depends on our eligibility trace. So we made an error in our evaluation. We thought we were going to get a piece of cheese and we got electrocuted. So how much do we update each of the states that we passed along the way? Well, we update all of the states in proportion to their eligibility trace. So the states that we just visited, or which we visited a lot, we assume are responsible for this big error that we just saw. And the states which we haven't visited for a long time, which we've never seen, don't get updated at all by this. Okay. And now we're just, so the eligibility trace is exactly the update we had from the previous slide, but we're now updating the value of all states in proportion to the eligibility trace. Okay. So this is the diagram for this. So now our guy, the agent, instead of looking forwards into the future, he's looking backwards over time. So he's building up this eligibility trace, and he's asking all these different states, what was your eligibility? What was your eligibility? How much did you contribute to this particular event that we saw, this particular error? And we update the value of each state in proportion to its eligibility, how much it's contributed to the error that we've seen. Okay. Does everyone sort of get the idea intuitively a little bit? Some people, some blank faces. Okay. So I don't have a lot of time. So what I really want to point out is that when lambda equals 0, then we only update one state, and that's the current state. So that basically happens because our eligibility trace, our update collapses to just is the state the current state. Because if it's not the current state, then if lambda is set to 0, then it just gets zeroed out. It's like a step function. Our thing goes up to 1 if it's the current state, and it drops off straight back down to 0 if it's not the current state. So it basically means that our whole update function that we had collapses exactly back to TD0, where we only update the one state that we're in, and we update that by alpha delta, which is exactly the update for TD0 that we just saw. Okay. And finally, I just wanted to say, okay, what happens? So we have about 5 minutes. Okay, so now we want to consider the other extreme, where lambda equals 1. What I really want to persuade you is that when lambda equals 1, this whole thing collapses to Monte Carlo, basically. So the way to think of this is imagine there's just some episode where we just visit some state once in that episode, and we visit it at time step k. So now we're going to have this eligibility trace, and it's going to be, this discount is going to collapse to just gamma. There's no lambdas anymore. And so if we never see that same state again, so we put up the state once, and now we're going to discount by gamma all the way down, and we're going to end up with gamma to the t minus k up to some step here. So the point I really want to make is that it turns out you can just accumulate these errors. You can come back and look at the notes, or maybe I'll do this a bit more next time. But essentially, what happens is that TD1 just accumulates all these errors online. So if we're actually adding up and wondering what happens to a particular state S, well, we can just add up all of these deltas from this time step onwards. Okay. So I don't have time to go through this, but what you get is this telescoping effect, where it turns out that all of these errors telescope together, and they all cancel out, and you basically end up collapsing with something which is exactly the Monte Carlo update that we get in Monte Carlo. So, TD1 is basically the same as Monte Carlo. The errors accumulated online step by step. And if you only were to do this offline, if you imagine that you update at the end of the episode, and you just updated your value function offline, so you wait until you get to the end of the episode, you don't do any updates, and then at the end you update, you add up all the updates you would have done, then you basically recover exactly the Monte Carlo algorithm. But if you actually did this online, so every step along your episode you applied your TD1 algorithm, you end up with something slightly different. Okay, so we end up with this view of TD lambda. We've got our backward view, our forward view. We've got, if lambda equals 0, in both cases this algorithm collapses to TD0. If lambda equals to 1, well, the backward view algorithm is this thing called TD1, which if you do it offline is exactly the same as Monte Carlo. And if you have just an arbitrary lambda between 0 and 1, you end up with something that's in this space in between the two. And we have the backward view TD lambda, that's what we mean by the TD lambda algorithm if you don't prefix it by anything. And the forward view kind of gave it this mechanistic, to give this theoretical understanding what it's doing. And it turns out that this telescoping still applies with TD lambda. And the final thing I just wanted to say is this theorem, which is that the forward view and the backward view of TD lambda are actually identical if you accumulate your updates offline. So if you have some agent that's walking through its episode, it's adding up what the update would have been at time step 1, time step 2, time step 3, but it's only when it gets to the end of the episode that it actually implements those updates. If you do that, then the forward view and the backward view of TD lambda are identical. They're mathematically the same. It's in the lecture slides if you want to see the proof. But in practice, we don't do that. In practice, we update online every step. You know, if you see some new information online, well, why not use it? We don't know. Okay, so that's it. That's all I wanted to say. And if you have a small step size, then it doesn't matter whether you do it online. Okay, next time we'll do control. We're going to